All right, it seemed that the most common error in the quizzes that I've just handed back was that students confused the idea of bulk modulus of elasticity with viscosity. And so remember that bulk modulus of elasticity is an idea that characterizes the compressibility of a fluid. So it's for a certain unit change in for a certain change in pressure, what is the unit change in volume? Whereas viscosity is talking about the relationship between shear stress and strain. And so viscosity and bulk modulus of elasticity are two separate properties. If you have other questions about the quiz, again, just like with the homework, feel free and come see me and we'll talk it over. Let's take a quick look at a couple of these announcements here. The homework number 2B is due on Tuesday in class, and we'll talk about a couple of these problems here at the beginning of the lecture. And then the lab that goes along with the surface tension is due on Tuesday in lab. And of course, that's an abbreviated report format where really all I'm looking for is the calculations and a brief discussion, as is mentioned in the handout itself. Lab number 3 that we're going to do is hydrostatic force, and we're going to break up into two groups for that experiment. We'll have group A at 2 p.m. and group B at 3 p.m. In the next slide I've listed the group assignments, and I think you've got it there in front of you. So that'll give us a little bit more hands-on opportunity if we break up into two groups for the experiments. Do you have a question?
The surface tension lab is due at your respective group time, or?
That's right, yeah. So group B has an extra hour to work on the lab report. And the sad thing is that I bet some students will be in a mad panic using that extra hour. So that's okay. I was a student too. I sometimes did things at the last minute. Although it's hard to remember why. It's just so much extra stress, but it isn't any less work. It's the same amount of work, maybe more. So here's the group assignments. If you ever are in a case where your favorite show is on at 3 o'clock and you want to switch with someone else in the class, I'll allow you to make those arrangements on your own. But we can't have everyone going to the 2 o'clock session each week. But if you can find someone who's willing to trade places with you, then that's fine. So next week, it's going to be A first and then B. The week after that, it'll be B first and then A. We'll alternate who gets to go at 2 o'clock. Problem 240. Let's talk about some of the key ideas of this problem. I'm not going to tell you the answer to it. For all I know, it's probably in the back of the book anyway, right, the answer. But what we will talk about is some of the key ideas so that we can try and figure out how this relates to the principles that have been talked about so far. This is a viscosity problem. This is a homework problem that's meant to illustrate the relationship between shear stress, strain, motion of an object, and how it would interact with the fluid. Where's the fluid in this problem? If you've read it already, where's the fluid? It's an oil. The oil is the fluid, but where is it? Anybody looked at this problem yet?
Yeah.
It's what? It's in the pipe, yeah. Specifically, there's this cylinder that's falling through a pipe, and the oil is in the small gap that's between the cylinder and the pipe. The cylinder has a diameter of 100 millimeters, and the pipe has a diameter of 100.5 millimeters. And so there's a gap. It's not just in two places. It's all the way around. They say in the problem statement to assume the cylinder is falling through the center of the pipe so that the gap is even all the way around the cylinder. And so there's an oil lubricating the gap between the cylinder and the pipe. What is given in the problem statement is the weight of the cylinder is 15 newtons. So that's based on whatever it's made out of. We already talked about the diameter of the pipe versus the diameter of the cylinder and how the difference between the two leads to a gap between them. The length of the pipe is specified, and we'll talk about maybe why that's relevant, why they've told us that. And then they've mentioned that it's SAE 20 weight oil. And in this problem, they say to use SAE 20 weight oil at 10 degrees Celsius. And I seem to recall from previous semesters that that might be off the figure. That there is in your book a curve that shows 20 weight oil, but I think the curve terminates prior to 10 degrees Celsius. I don't remember exactly, but that's sort of in the back of my mind. And so what I'll do is I'll just tell you the viscosity you should use for the oil is 0.35 newton seconds per meter squared. That's not in the problem statement. That's me giving you that information right now. All right, so it says in the problem statement that it's undergoing a steady rate of descent, and they want you to know what is the velocity. So the cylinder is falling down. Why is it falling down? What's causing it to fall through the pipe? It's gravity, yeah. And so its velocity is downward. What are the forces involved? Well, the forces are the gravity, the gravitational forces. The weight of the cylinder is down, and so as it moves downward, shear forces are resisting its downward movement, and so the shear forces are pushing up. If it's in equilibrium, and the hint here, the real big part of the problem that is buried at the first part of the problem statement, so maybe it would have been easy to miss, is they say steady rate of descent. And so what hint does that give us when it says steady rate of descent? Okay, it's moving downwards, and what's its acceleration? It's zero. The velocity is constant. The acceleration is zero. It's a steady rate of descent. And so that means it's in equilibrium. Equilibrium is important because this cylinder that's falling downward has a weight of 15 newtons. And what that means is that there is a shear force, I'm going to call it the force due to shear, that's pushing up, and it's also 15 newtons. If it was anything other than that, then the velocity would be changing if there was an imbalance in the forces. But since the forces are equal, it continues to move downward at the same speed. Any questions so far? All right, so this is the equation we have for shear force. I told you already that because it's in a steady rate of descent, it's falling at the same speed. That means that the forces are in equilibrium. Now, by the way, it's not just in this one location that the shear force is applied, right? Where is the shear force applied, Elman? For this cylinder, if we had a cylinder, do you mind if the cylinder's falling through a pipe. So the oil is pushing up on the cylinder. Where is it pushing up on the cylinder? It's all around it. It's all around it that the oil is pressing on the cylinder. And so me having this arrow here is just basically to show the direction of the force. It's acting all the way around this circular cylinder. All right. So the shear force equation is area, viscosity, du, dy. And so that's the formula we need to put in. And what's the question? Find velocity. So what's the unknown in this shear force equation? Du, exactly. What is the velocity? U here is the variable we're using to represent the velocity. So what area should we use? Elman already identified it's the outside area of the cylinder. And the information is given to you in order to calculate that outside area of the cylinder. Students sometimes make the mistake of thinking, oh, it's this area. It's pi r squared, right? Because you could do that, or I told you not to use r anymore. So what if you said the area is pi d squared divided by 4? That's the formula for area. But that's the formula for the area that isn't the interaction we're talking about. We don't care so much about the oil being on the top of the cylinder or the bottom of the cylinder. What we care about is where the oil is in contact with the outside of the cylinder. And so you'll need to calculate the outside area all the way around of that cylinder and substitute it in there for A. The viscosity that you should use has already been provided, 0.35 newton seconds per meter squared. Zachary said that the velocity, the unknown, is du. Now what about dy? When we had that plate in the tank example previously, where we're trying to pull a plate through a tank of glycerin, what did we use as the distances in that problem? What was dy there? Yeah, we used the distance top, distance to the bottom. And so we had two solids, and between two solids was a liquid. It was a solid tank and a solid plate, and between the two solids was a liquid. And so the gap distance, the dy we used, was the distance between the two solids. You can do the same thing here. Find out what are the two surfaces that are interacting. It's the surface of the cylinder interacting with the surface of the pipe, and between them is that oil that's connecting them. And so you need to find out the dy distance between those two surfaces. And I don't want to give too much more away than I've already given you, but I think all the key points are there to be able to solve this relatively easily. Any follow-up questions on this problem you want to ask before we move on? All right. We already talked about bugs and surface tension. You have the problem in your assignment that says, here is a six-legged bug. Each of its leg is 5 millimeters. What's the maximum mass of the bug that will enable it to continue to float on the water? And so I just wanted to remind you that the surface tension force, a formula, is the surface tension constant times length. And so the example that we did in class, the length in question for those glass tubes, the water was rising up in the glass tubes. In that example, the length was the circumference around the glass tube. In this instance, the length is going to be the length of the bug's legs. And remember that since the bug's leg breaks the surface in two locations, that you need to double it. Same as for the lab. And so this should be very similar to what you did or you're doing for the calculations on the lab, because you've got total length. You can look up the surface tension for the liquid that's specified, and then find out for the force. What's the relationship between force and mass, by the way? If you calculate the force from the surface tension equation, it says to find the maximum mass of the bug. mg, right? So once you find the force from that equation, divide by g, and that will tell you the mass of the bug. Any questions on that one? All right, so from time to time, I'll see a problem that I think needs a little bit of discussion in class, and we'll spend a few minutes going over the key ideas. We won't have time to do that on all the homework problems. Some of them I intentionally want you to struggle with, because that's how you get stronger, is beating your head up against the wall of the really tough problems. But then sometimes I won't want you to chase your tail for so long. So anyways, let's move on to talking about vapor pressure. All right, so who would be, well, Levi, what are we seeing in this picture here? Describe this. Water boiling in a coffee pot. I couldn't have said it better myself. Exactly right. And so what do you, what would you infer from this picture? What's the temperature of the water? 100 degrees Celsius is exactly right. How did he know that it's 100 degrees Celsius, Kia? Just lucky guess? Explain his reasoning, because I think there was more there than a lucky guess. How did he know it was 100? He's right. It sure does. What if this was a coffee pot on top of Mount Everest? Could we make the same assumption that it's 100 degrees Celsius? What do you think, Zachary? No, probably not. Well, we're going to talk about there's a relationship between boiling point, vapor pressure, and the pressure of the atmosphere above the liquid. So this just illustrates that one way to get water to boil is by heating it. But that's not the only way you can get water to boil. That's the most common way that we see most often. You boil water by heating it. By the way, you know, when you boil water and you see little bubbles from boiling water, you know those little bubbles down there? What are those little bubbles? Are those little air bubbles? What are they? It's a gas, right? If there was a little miniature person, like if you got Honey, I Shrunk the Kids, you know? You got really small and the temperature didn't kill you, but you wanted to go down there. Could you breathe that? Those little bubbles? Why not, Alex?
Are they like hydrogen, oxygen, where the molecules break apart?
You're thinking of electrolysis, which is when you electrify a solution. And that's a similar thing to this, and you're on the right track, but no, they're not hydrogen and oxygen. It's H2O vapor. It's not air. It's not oxygen and nitrogen. You know, the atmosphere we breathe is a mixture of oxygen, nitrogen, and a lot of other little things. Those little bubbles, those are water vapor bubbles. That's H2O. That's vaporized H2O. So we can't breathe vaporized H2O. So at sea level, water boils at 100 degrees Celsius. At Mount Everest, water boils at 69 degrees Celsius. If you've ever baked a cake before and you're really studying the back of it, you know, just trying to pass the time till you get to eat the cake, you'd notice that it has high altitude instructions on a lot of cake mixes. And it'll usually say something like, you know, above 3,500 feet, add an extra egg and you know, another quarter cup of water, something like that. They adjust the recipe somehow, and it usually has to do with the amount of liquids that should be put into the recipe if you're above a certain elevation. And the reason why they have high altitude instructions is that at high altitudes, water vaporizes at a lower temperature. And so, in other words, water boils more easily on Mount Everest than it does at sea level. You don't have to put as high a flame to get the water to boil. It starts to vaporize, to go from H2O liquid to H2O vapor with a less amount of heat. So what is this property of vapor pressure? Vapor pressure is the pressure at which a liquid will boil. And what we were just talking about was the temperature at which a liquid can boil. But the reason why water, it's not that water transforms itself magically at the top of Mount Everest. It's still H2O. It's just that what's different about sea level versus Mount Everest, if here is the sea and then there's a mountain all the way up to top of Mount Everest. Okay, here at sea level, the air is pushing down on water a lot, but at Mount Everest, the air pressure is lower. They say that it's very difficult to breathe at high elevations because the air pressure is lower, and it's not that there's less oxygen. Here at the top of the mountain, it's still 80% nitrogen, 20% oxygen. It's not that the recipe of what's in the atmosphere is any different. It's just that the amount of nitrogen and oxygen is lower, and so there's less pressure. It's pushing on your lungs with a smaller force, and so you can't get as much of it into your system. And so since the atmospheric pressure is lower, then the water has an easier time escaping. It vaporizes more easily because the pressure of the water is able to overcome the pressure of the atmosphere. And so vapor pressure, you can think of it as water's always trying to escape from the liquid phase into the vapor phase. There's little molecules in the coffee pot. The molecules of water are bouncing around, and when you heat up the water, you're making those molecules move around faster. You're adding energy to the system. And they move around faster, they've got more kinetic energy. If you heat it up and they're moving around fast enough, then some of those molecules will have enough kinetic energy to escape the barrier, to get through that membrane that's at the top of water. Remember that water has a surface tension that keeps it all together. If a molecule has enough kinetic energy, it can escape through the membrane and vaporize, so that when you have a low pressure environment, it doesn't require as much kinetic energy for the random water molecules to escape into the vapor pressure, into the vapor phase, into the atmosphere. So vapor pressure is talking about, for any particular liquid at a certain temperature, how much it's trying to escape into the air. Vapor pressure increases when temperature increases, and so that's what I was just talking about with the increased kinetic energy, the molecular activity of the solution. As you increase the temperature, molecules are banging into each other, and one of them will get enough collisions that it has a lot of energy and it can escape through the barrier and vaporize. And so here is a graph, a table that shows the vapor pressure of water at different temperatures. So we can see at 100 degrees Celsius, the vapor pressure of water is equal to 760 millimeters of mercury. And that's the same thing as the atmospheric pressure. That's how 100 degrees was defined. It's not a coincidence that water boils at 100 degrees. They said, let's have a temperature system where water freezing defines 0 and water boiling defines 100. That was intentional. And so 1 atmosphere, or 760 millimeters of mercury, is where water vaporizes. So can you think of a liquid that vaporizes more easily than water? Alcohol vaporizes more easily than water. Very good. Gasoline is another thing that if you pour a gallon of water on the pavement and a gallon of gasoline, the gasoline will evaporate more quickly. That's because it has a higher vapor pressure. It's somehow more anxious to get into the vapor phase than to stay in the liquid phase. There are some liquids like mercury that have a lower vapor pressure than water. Oil doesn't evaporate as quickly as water does. So vapor pressure is just a fluid property that describes the tendency of a liquid to want to vaporize. So here's an illustration of, it's not a linear response. As you increase the temperature, the vapor pressure increases at a greater rate as the temperature goes up. It's kind of interesting if you look at this, that even frozen water has a vapor pressure. And so there is evaporation from ice. If you have a lake that has ice on the top of it, the ice will evaporate. And that process of going from a solid to a gas is called sublimation. You may remember that vocab word from chemistry. Sublimation is a process of solid to vapor. It's very slow, but you can have, like if you put a frozen t-shirt out on a line and it stays freezing outside, eventually it'll dry off. Water can boil if the pressure is lower than the vapor pressure. So we're going to watch a video of water boiling at room temperature. And the reason why the water can boil at room temperature in the video we're going to watch is that they have a cup of water, and you need to think about the water molecules have some tendency to try and escape. Their escape tendency is P sub V, vapor pressure. The atmospheric pressure is trying to keep them in. The atmosphere is trying to keep those molecules in the liquid phase, and so P atmosphere. When you heat up the water, okay, when it's cold, when the water's cold, it has a small vapor pressure. When you heat up the water, the vapor pressure gets bigger, and once those two pressures are equal, when P sub V equals P atmosphere, then the water will start to boil. And by boiling, that means that in general, throughout the liquid, it's not that it all instantly, boom, poof, goes into a big cloud of water vapor. It just means that the two pressures are equal. There is evaporation even before you get to the vapor, before you get the vapor pressure equal to atmospheric pressure. water will evaporate at 20 degrees Celsius, even though at 20 degrees Celsius the vapor pressure is only 17 millimeters of mercury compared to 760 of the atmosphere. Water evaporates faster as you increase the temperature. If you heat something up, like the reason why in the clothes dryer, you add heat in the clothes dryer because it evaporates more quickly at an elevated temperature. And so heating it from 20 to 60 degrees is going to almost increase evaporation by coming close to 10 times as quickly. Okay, so I've got the link to the video here. We'll watch water boiling at room temperature.
We're going to demonstrate reduced pressure boiling by creating a vacuum in a glass vacuum jar and using an Edwards pump. By using and applying vacuum, we're making water change from liquid to vapor very quickly and very effectively. Water at room temperature is placed into a beaker before putting it into a glass vacuum dome. We now open the vacuum isolation valve. You can soon see the vacuum gauge showing around 20 millibars of pressure. This is significant because it's the vapor pressure of water, and therefore the point at which it will boil at room temperature. At atmospheric pressure, water boils when heated to 100 degrees Celsius. That's because it's the point when water vapor pressure is equal to atmospheric pressure, and water begins to change phase from liquid to vapor. In this demonstration, we don't add any heat, but instead reduce the pressure. When this pressure is equal to the water vapor pressure, the water boils or changes phase, but at a much lower temperature. In fact, the energy for boiling is coming from the water, and consequently its temperature reduces. And as the pressure becomes lower, the water will eventually freeze. You'll see that even when removed from the vacuum chamber, the water remains frozen. A simple process, but one that's widely used in the pharmaceuticals and food packaging industries.
All right, that kind of just blew my mind. It boiled until it froze. Now, water boiled until it froze. How do we make any sense of that? Anybody want to recap why it boiled and then why it froze? Why it boiled is maybe the easier thing to explain. Morgan, why was that water boiling? Okay, the vapor pressure was high, the atmospheric pressure was low. How did they make the atmospheric pressure that was in contact with the cup of water? How did they reduce that? Yeah, that vacuum was enclosing the cup. So they pumped out atmosphere. So what they were doing, they weren't increasing the vapor pressure by adding heat. That was the coffee pot. The coffee pot strategy was increase the vapor pressure by increasing the temperature. The vacuum bell decreased the gas pressure so that it was less than the vapor pressure. So that's why it was boiling. Anybody in here take thermodynamics yet? Why did it freeze? Why did the water freeze? I think the people who've taken thermo are maybe in the best position to explain that. I've never taken thermo, so I'll take a stab at it, but I was hoping maybe one of the thermo guys could bail me out. Yeah, I didn't take it. Oh, no. Are you kidding? Two engineers talking about engineering? No. All right. The reason why it froze is in order to change phases requires energy. For example, if you have 0-degree ice, you have to add heat to turn it from ice into a liquid. Just the phase change itself requires energy. And so if you're going the other way, if you're going from water, if you have water, for it to go vaporizing, it requires energy as well. And so it's the phase change energy requirement, and so it was decreasing the temperature of the water because it had to get that energy to sort of pay for the phase change from somewhere, and it got it by steadily reducing the temperature of the water until it was solid. So don't worry about that aspect of it. Hopefully that'll make more sense when you take thermo. But until then, what I would like you to just keep in mind is that you can boil water by reducing the pressure of the atmosphere that surrounds it. So that's what's happening at the top of Mount Everest. Why it boils more easily is there's less atmosphere, so the vapor pressure is able to overcome the effects of atmosphere more quickly. So here in the table that's also found in your book, you can see that the vapor pressure of water is a fluid property that you can look up for any temperature you'd like and interpolate in between the ones that are given. All right? Here, the vapor pressure is given in units of newtons per square meter. In other words, in units of pascals. Any questions about vapor pressure? So why is it important? Well, it's important in case you want to put a cup of water in a diving bell and pump out all the atmosphere and watch it boil. You know, there's other applications besides that sort of strange contrived lab illustration that was just shown. One of the reasons why vapor pressure is important is in hydraulic engineering. Sometimes we use dams and reservoirs to provide hydropower. And this is a big dam in Russia, and I can't say the name of it. Sayano-Shushenkaya. So I just proved I can't say it. I don't know what it's called, but about, I think 5 years now, there was an incident at this hydroelectric power station where previously they had a real nice dam and hydro facility that electricity was being generated, and water that's moving very fast because of Bernoulli's equation. We'll learn later in the semester that when you change the velocity of a liquid, you also change its pressure. And in this dam, they changed the velocity of the water that's flowing through the dam so quickly that actually the water vaporized. And that process of vaporization is called cavitation, and those tiny little vapor bubbles that are in the water over time caused a gradual erosion in some of the pipes that were leading water from the dam through the hydro station, and it all blew up all at once, and about a dozen people died in that incident. And so it's just an illustration, and there are dozens more like it, of where the vapor pressure of water causing cavitation, as it's called, has an unintended negative consequence. So that's something that we'll revisit in hydraulic engineering as well when we talk about how to avoid cavitation so that you don't have incidents like that. All right, well, moving on. Done with vapor pressure for now, starting to talk about pressure intensity. Just in general, pressure in a liquid as you go down deeper. One of the questions I asked you to address in that getting to know you assignment that you gave me is what's the deepest point of the ocean, what's the highest pressure in the ocean? And so what is pressure? Pressure intensity is actually the phrase that we ought to use. It's a scalar, meaning that it acts in all directions equally. The units of force per area, newtons per meter squared, or pascals. If you're down deep in the ocean, then the pressure is acting in all directions. And so it's not like if you're under the ocean, you can turn your head and avoid the pressure. You know, like your ears, when you're under the pool, start to hurt. And it's not like they only hurt if you're looking up at the water and you can shield yourself by looking down. The water pressure is from all directions equally, regardless of your orientation in the water. And so, based on what I just said, you've got a narrow reservoir and a very wide reservoir. They're both the same depth to the bottom. So which of these has the higher pressure at the bottom? Would it be the big reservoir, or would it be the narrow reservoir that has the higher pressure at the bottom? Okay, we've got to vote for the narrow reservoir. Any other ideas? Why do you think they'd be equal? They have the same depth. It's the water above that matters. It's not the water to the side. And so if you have a very narrow well and you dive 20 feet down in a narrow well, you're going to feel the same pressure as if you dive 20 feet down in the ocean. So it was kind of a trick question. They have the same pressure at the bottom of both of these reservoirs. The pressure only is a function of the depth of the water above you, not the amount of water on either side. So the hydrostatic equation is what describes the change in pressure as you go through a liquid. And here we have a tank, and we're going to be measuring elevations in this tank relative to a horizontal datum. We'll call it the Z datum at the bottom of the tank. The hydrostatic equation is shown as dP divided by dZ is equal to negative of gamma. And gamma is a variable that we've seen before. Anybody remember what gamma is called, the name of it, that variable? Unit weight. Sometimes we call it the specific weight. In the quiz, I asked you what's the density of water. I don't require you to memorize too much, but a couple of things you should memorize is the density of water. You probably already have now. If you didn't get it right on the quiz, you'll never forget it again. Another thing you should memorize is the unit weight of water. So does anybody already know what the unit weight of water is? What's the value? Or just the units maybe? Kilograms per meter cubed is density. Yeah, so density is 1,000 kilograms per cubic meter. What about unit weight? No, it's not kilograms per meter squared. The way that we get it is it's the density times G, if that gives you a hint. So if it's 1,000 times G, the magnitude of the unit weight will be 9810. And so it's going to be kilogram meters cubed times meters per second squared. So it is newtons per meter cubed. Okay, so a kilogram meter per second squared. So kilogram times a meter per second squared, those combine into Newton, and then what's left over is per cubic meter. So it's 9810 newtons per cubic meter. And so a cubic meter of water, that's a volume. 1 cubic meter of water weighs 9810 newtons. So a cubic meter of water has a mass of 1,000 kilograms, or a weight of 9810 newtons. And that's the typical value, you know. In the absence of any temperature value, we say 9810. So that's just sort of reviewing what unit weight is. Now, let's jump back to the hydrostatic equation. What is that formula saying? It says that as you're in the water, dP divided by dZ. Let's say I'm going down in the water from the top of the tank. What is the hydrostatic equation saying? If I'm here in the tank and I'm going down through the water, dZ is decreasing, so pressure is going to be increasing. So dP is equal to dZ times negative gamma. So if dZ is going down, so if I have a decreasing dZ, so a negative dZ, multiplied by negative gamma, that means that the pressure will be increasing at a rate of 9810. So let me write it in words as, in water, this is something you should copy down. In water, pressure increases at a rate of 9810 newtons per meter squared per meter of depth. So there was a question of, isn't it meters cubed? And it is. it's 9810 newtons per meter squared per meter of depth. So if we go down 1 meter, so 1 meter change in depth multiplied by 9810 newtons per meter cubed. So if you go down -1 meter and the pressure is accumulating at negative gamma, then that means that your dP, the change in pressure, is a positive 9810 newtons per meter squared. The depth, the change in Z, right. So what about if you go up through water? How does the pressure change as you go up through water according to the hydrostatic equation? So a positive dZ means that the dP will be negative, the negative sign. So the pressure is decreasing as you surface, as you move towards the surface in water or any other liquid. This is called the hydrostatic equation, and hydro implies water, but the hydrostatic equation works for any liquid. And in fact, it's also valid for gases, so it's valid for any fluid. That we can say the pressure changes as we go up or down. And so it works even for the atmosphere. Remember the drawing I had, really detailed drawing of Mount Everest? So the reason why the pressure is lower at the top of Mount Everest is we have been going up through a fluid. The fluid is the gas, it's air. You know, air has a density. The density of air for water, it was 9810 newtons per cubic meter. The gamma for air is, I think, about 1.2 kilograms per cubic meter times 9.81 meters per second squared. So, you know, it's about 10 newtons per meter cubed. So what if you go from ground level up a building 100 meters? How is the pressure going to change? According to the hydrostatic equation, up 100 meters in air, what's the delta P? So we could use this hydrostatic equation to say the delta P is going to be delta Z, and then it will be negative gamma. So if we're going up 100 meters in air, the delta Z is 100 meters. The negative gamma is about 10 newtons per meter cubed. And so that means that the change in pressure is going to be 1,000 newtons per meter squared. That's 1,000 pascals as you go up. Has anybody had their ears pop on an elevator before? I went to Atlanta over the summer and stayed in a hotel that's very, very tall. It's the tallest hotel in the United States, as a matter of fact. It's in Atlanta. And as you go up in the elevator, my ears would pop 3 times. I knew I was getting close to my floor. My ears popped for the 3rd time. I didn't even have to look at the indicator in the elevator because it was 1 pop, 20th floor, 2 pops, 40th floor, 3 pops. There I am, ready to get out. So the pressure changes as you go up through air. That was that the pressure is negative. So it decreases as you go upward. 1,000 pascals for every 100 meters. Yeah.
Does pressure change, like, say you're swimming at the bottom of the ocean, but it's possible, would it be harder than swimming at the top?
Oh, that's a good question. So, like when you say harder to swim, you're thinking about like, you know, like moving your arms. Do you have to stroke harder?
Yeah.
And that would depend on the density of the liquid, and not pressure, right? And so the density of the liquid, water is, we've already talked about, basically incompressible. And the pressures at the bottom of the ocean aren't enough to compress water very much. A little, but not much. And so it might be a little bit harder to swim, but probably it wouldn't be noticeable, just because water is mostly incompressible. It would be harder to swim because it would be collapsing your lungs, though.
Yeah.
But if you set that aside, it's just like about the forces on your hands, then no. And you know, it's actually true that it collapses your lungs. There are people who, it's this sport, free diving, I think it's called, where you hold your breath and you see how far you can go under, and they go down far enough that the pressures really like decreases the volume of their lungs by 60, 70%, something like that. So it kind of squishes them a little bit.
Does pressure depend on temperature?
Yes, it does. Why would pressure depend on temperature? Is because density is a function of temperature, and especially for gases. Gases have their density vary quite a bit more. And so if you're going down through hot water, remember the density is low. The density decreases for elevated temperatures. So if you're going down through hot water, then you'd expect the pressure change to be less than if you're going down through cold, more dense water.
So if they're like way more Mount Everest.
That's true, yeah. So temperature would have an effect on the pressure there, yeah. Right. All right, so we've already talked about the units associated with the hydrostatic equation, and hopefully those units make sense, where pressure, remember, is units of pascals. A pascal is a Newton per meter squared, and unit weight was newtons per meter cubed, and elevation change is units of meters, and so it all works out. Okay, assuming that density and specific weight are constant through a fluid, which is a valid assumption as long as it's the same fluid that is not compressible, you can integrate the hydrostatic equation, which is what we've just been doing really. We've been taking it from point to point, in other words. You can get piezometric pressure. And so piezometric pressure, here you've got P plus gamma Z is equal to PZ. And so the pressure at a certain point plus gamma Z. Let's talk about a tank of water. Let's go back. All right. So if we have a tank of water, remember that we're measuring elevation according to some elevation datum. It doesn't matter where this elevation datum is. It could be at the bottom of the tank or the top of the tank. What I mean is just we're measuring our elevation according to some location that is being held steady. We're going to say this is our starting point for elevation. So everything above it would be a positive elevation. If we are here at location 1, we can calculate the piezometric pressure at location 1. That would be the pressure that there is here. And so the pressure depends on how deep it is underwater. And then we're saying there's also this other term that is gamma Z. And so we'd look at how high above the vertical datum is the location in question, and we'd multiply that by gamma. That's piezometric pressure. That's the definition of piezometric pressure. Is it depends on what datum you're picking, because you're going to be measuring how much additional distance is underneath the point in question. And that's what this is basically dependent on how much distance is above it. The pressure depends on how deeply immersed a point is in liquid. And then the second term in piezometric pressure, the gamma Z, is taking into account the distance underneath it. And piezometric pressure becomes important in later chapters when we start talking about flow measurement.
So it depends on what's above the angle.
Exactly. And so it's very critical that you keep in mind where is the datum when you are computing piezometric pressure. Piezometric head is another way of saying the same thing. If you look at both of the terms here, if you divide by gamma, so pressure divided by gamma plus gamma Z divided by gamma, that's what this is. And so rather than having units of pressure, where each term in this equation, the pressure plus gamma Z, is going to have units of newtons per meter squared, the units of both terms here is going to be meters. So Z is a distance in meters, and then if you divide pressure, which is newtons per meter squared, by gamma, which is newtons per meter cubed, what's the units of the resulting combination of those two? It's just equal to meters. So piezometric head is keeping account of for a certain fluid, again, what's the pressure there? What's the elevation above the datum? But it's just expressed with different units in terms of a head rather than in terms of a pressure. Between 2 points, if we find the change in piezometric head, it's called the hydrostatic equation. So the hydrostatic equation says between point 1 and point 2, there's the same amount of piezometric pressure. It's just something's being exchanged between the 2 points. Look at the sum of pressure divided by gamma plus Z1. This has Z1. It's got a lot of Z1, but not very much pressure because it's not deeply immersed in the water. So P1 here is going to be relatively low at 1. But at 2, since it's more deeply immersed, P2 is going to be greater, but it has less Z2. So between point 1 and point 2, the increased pressure that there is at 2, the pressure at 2, it's greater than the pressure at 1. Well, where did that extra pressure come from? It came from the delta Z. The change in elevation is what causes the increased pressure at location 2. Let's try this with an example. I'd like you to get out some paper and your calculator and a pencil and calculate what is the pressure at location 2. I haven't told you the unit weight of the water. What should you use for the unit weight of water in this case? 9810 newtons per meter cubed. Right, because I don't say any special temperature, so you just use the default value. We already know the pressure at location 1, and we're given the absolute elevation. Well, I guess it's a relative elevation. All elevations are relative to a datum. So we know that the elevation at location 1 is 34 meters, the elevation at location 2, 26 meters. Okay, so we're starting off with a hydrostatic equation. Okay, P1 is given as 66,000 newtons per meter squared. Okay, Z1 is given as 34 meters. Z2 is given as 26 meters, and P2 is not known. Okay, so we can rearrange the hydrostatic equation to solve for P2. That is P1 divided by gamma plus Z1 minus Z2, and all of that multiplied by gamma. Okay, so it's 66,000 newtons per meter squared divided by 9810 newtons per meter cubed plus 34 meters minus 26 meters, 9810 newtons per meter cubed. So the pressure at 2 is 144,480 newtons per meter squared. In other words, the pressure at 2 is 144 kPa. Kilopascals is probably a new unit for you. You're probably not accustomed to thinking in terms of kilopascals. Maybe what would be more common in our reference is thinking in terms of PSI. Just to give you an idea of how big is 144 kilopascals, in the pipes that flow underneath the road, the typical operating range for a municipal water pipe is between 250 and 850 kilopascals. And so it's actually less than the water pressure in a pipe. So
Is that what comes out of like a fire hydrant?
yeah, what comes out of a fire hydrant will, ballpark usually be about 500 kPa out of a fire hydrant, or out of your hose. Any opening in a, or the shower or the tub. All right. Any questions about this example or the hydrostatic equation? If we just want to know the pressure change between 2 points, we can abbreviate the hydrostatic equation. The full version of the equation is to say, what's the pressure at 1? What's the elevation at 1? What's the pressure at 2? The elevation at 2? What this abbreviated version says is, well, let's just think about it in terms of a change in elevation. So there's now a delta H between the 2 points. And instead of saying P1 minus P2, it's just saying a delta P. So we have a change in pressure between 2 points with that hydrostatic equation. And so before we do this other one, how would we apply this abbreviated hydrostatic equation to the same problem? So what was the change in pressure between those 2 points in the reservoir? All right, we've got 8 meters of elevation, so delta H is 8 meters. The unit weight of water, because it said delta P is delta H times gamma. So the unit weight is still 9810 newtons per meter cubed. So the change in pressure will be 8 meters times 9810 newtons per meter cubed. So somebody with a calculator can tell me what's that delta P? 78,480 newtons per meter squared. So that P2 is P1, now should I say plus or minus the delta P to find the P2? How do you know it's plus delta P? Right, right. It's funny, when we start getting into something called manometers, it seems really obvious now. Obviously, the pressure increases as you go down. But the book has some problems that will cause you to forget that. They're complicated enough that you'll think, oh, now what's this point up here? Is it going to be more pressure or less pressure? Pressure always increases as you go down through a fluid and always decreases as you go up through a fluid. So P2 is going to be P1, which was 66,000 newtons per meter squared, plus the change, 78,480 newtons per meter squared. And so P2, if we add those up, it should be 144,480 newtons per meter squared. So the same answer either way. It's just that in this abbreviated approach, we were concerning ourselves with the change. And then the pressure at 2 is the pressure at 1 plus the change. Okay, now, what about this Challenger Deep? If it's 10,000 meters underwater, what's the pressure there? It's been a while since I heard that ringtone. Not as popular as it used to be. It used to be that's everybody's ringtone. Now it's just a few people. All right. It's an oldie but a goodie. So apply the hydrostatic equation, the abbreviated one, to find the pressure at the bottom of the Mariana Trench. How would you find the pressure in pascals? What's the pressure in pascals at the bottom of that trench? Seawater is 10,100 newtons per cubic meter. And since I've got some time, I'll go ahead and put the exponent on that. They make an HP 48 app for both Android and iPhones if you want to come over to the dark side of not using Casio calculators.
That's the blue one that used to beep at you.
Exactly. Yep. You did not want to hear that beep. All right, 1.1, let's see, 1 times 10 to the 8th newtons per meter squared. Is that right? 1, 2, 3, 4. Yeah, 1.1 times 10 to the 8th newtons per meter squared. And so it's pretty high pressure down there. If we have it in terms of kilopascals, that's 110,201 kPa. So remember, I said that a typical municipal water supply will be at 500 kPa. This is at 110,000 kPa. So a pipe will start to break at, well, the most sensitive thing in a pipe network is usually people's water heaters. That's what will leak first. If pressures are too high, people's water heaters start to leak. And you can have a water heater leaking maybe in the range of 1,000 kPa. So this is 100 times greater than that, 110 times greater than that. So it'd be a thick submarine to get down that deep. That's it for today. Any questions about the hydrostatic equation? Let's take one parting look at the announcements and make sure that we're all up to speed on where things are headed for next week. The homework assignment is due in class on Tuesday. I've got office hours from now until the end of the day, and I'll be in my office for much of tomorrow as well. I've got a couple of meetings in the afternoon, but I'll be in my office for most of the morning if you'd like to stop by. And of course, if you have questions during the weekend, you can send me an email and I'll do my best to respond. I don't always take my notes home with me, so sometimes I'll try and be responding from memory. So if you do write a question, it helps if you're detailed as possible. Like, don't say, in the third problem, how do you know what density to use? I don't know what the third problem is. Or, so the point is, if you want to send me an email, I'll do my best to respond, and it's helpful if you write a detailed description of your question. Surface tension lab on Tuesday, and we'll do the hydrostatic force lab on Tuesday afternoon. I'll give you that handout in class on Tuesday. Any questions? All right, I'll see you on Tuesday then.